I'd like now to talk about the Wittig reaction. And the Wittig reaction is actually in two parts. First of all, the formation of the Wittig reagent, which is brought about by the reaction of triphenylphosphine with an alkyl halide, and then treatment with N-butyllithium to form the Wittig reagent. Then this Wittig reagent is reacted with an aldehyde or ketone to form an alkene and triphenylphosphine oxide as products. Alright, I want to show you the mechanisms for those processes. And we'll start off with this alkyl halide, which can then be reacted with triphenylphosphine. And what this does is it forms a triphenylphosphine salt, where the triphenylphosphine is replaced for Br, and the Br negative is now the counterion to the positive charge on the phosphorus. This can then be treated with N-butyllithium, which is a very strong base, and that gives this kind of thing. Which has a positive on the phosphorus and a negative on the C. And then this is actually in resonance, where the negative goes in to form a double bond with the familiar form of the Wittig reagent. Alright, so let's look at the mechanism for that. So the mechanism for the first part has the phosphorus coming in and displacing the bromine. Now the way this works is that phosphorus is in the same group as nitrogen on the periodic chart, so it can actually act as nitrogen does and displace leaving groups nucleophilically using a lone pair. That leaves a positive charge on the phosphorus, and this Br negative will be the counterion to the phosphorus here. Then we can use a very strong base, something like N-butyllithium. This is N-butyllithium here, without the lithium part, but the lithium part is just a counterion, the Li+. And this is a very strong base. The reason for that is because it's the conjugate base of an incredibly weak acid, butane. So this would love to grab a hydrogen and form butane so it can just float away. Oops. And that will give us this. Now the reason this forms, aside from butane being a very strong base, is that we are forming an anion that is stabilized by an adjacent positive charge. So we've got a negative charge here that is stabilized to a large degree by the phosphorus, which has a positive charge on it. So remember that anions can form when they're stabilized by something. And then, as I mentioned, this is in resonance with the double bond form that we talked about earlier. Alright, so that's how we get our Wittig reagent. Now what I'm going to do is show you how the Wittig reagent interacts with an aldehyde or ketone. So we'll choose this as our ketone, and we will react it with our Wittig reagent. And the product we're going to get is going to be this one. Plus triphenylphosphine oxide as a byproduct. Alright, let's look at the mechanism for that. So we'll start off with the C double bond O, and then we'll interact it with the Wittig reagent. Now the reason that this works, I'll show you the mechanism and then I'll give you an explanation for it. And what we get is what's called a phosphooxetane. And this forms because if you look at the way that the delta pluses and delta minuses pan out here, we've got a PPH3 which has a delta plus and a C that has a delta minus. And we know that because of what we see up here in the resonance structures for the Wittig reagent. And on the C double bond O, we know that this is going to be a delta minus and we know this is going to be a delta plus. So we can see how those might be attracted to each other. So we end up getting this phosphooxetane structure here. And then this can fall apart pretty easily to form our triphenylphosphine oxide. Whoops. And our alkene. So you can see what the alkene looks like. It's going to look like this. And you can see that's the new double bond forming right there. And then you'll have this triphenylphosphine with the P double bonded to the oxygen. Now this is a very stable bond, P double bond O. So what happens is we get to this compound and it can't reverse. It forms and that's the way it stays, and then everything just pulls through to get the alkene at the end. So the driving force for the reaction becomes the formation of this very stable compound that has the P double bond O. And there you go, that's your mechanism for the Vedic process.